on noisy intermediate scale quantum hardware by variational trotter compression. Go ahead.
Thank you very much, and thanks for giving me the opportunity to talk. So my name is Peter Orth. I'm an associate professor at Iowa State University and scientist at Ames Lab. I'm part of SQMS. This work was done together with my former undergrad, Noah Berthusen, who's now pursuing graduate studies at the University of Maryland. My postdoc, Thais Trevisan, and my colleague, Tommy Adekola, was also a part of SQMS. So the title was read. So this is about near-term applications, particular variation approach to quantum dynamics simulations. Let me see how I can move forward here. Okay. So I think after Nathan's talk, most likely this slide is not needed. Nevertheless, let me introduce the problem that we are addressing, which is quantum dynamics simulations. So typically, we start from an initial state, which, for example, you can write as a generic, say, superposition of energy eigenstates of a many-body Hamiltonian H, which you may not know, but you can write the initial state like this. And then under dynamics, all these eigenstates get phases e to the minus I, E, and T according to their energies. And so the state becomes pretty complex. And the dynamics of observables and correlation functions, what we're typically interested in condensed matter, I'm a condensed matter theorist, are exhibiting this oscillating behavior where the energy differences between states M and N, when there's a finite matrix element of a corresponding operator is present, occurs. So now we all know that this is a classically hard problem due to, in general, rapid growth of entanglement in non-equilibrium for generic, let's say, non-integrable Hamiltonian H. And so the reason is physically that this sum here may contain highly excited states, for example, if you perform a quench. And so the system will exhibit volume law entanglement entropy, and there's no efficient classical algorithm to deal with this because entanglement equals complexity of a classical simulation. However, this is no longer true for quantum computers. And so there is an opportunity in this problem for quantum computing, as we have discussed in some detail before. So now this slide is giving kind of like an overview of quantum algorithms for dynamic simulations. And I think, again, after Nathan's talk, this is probably not necessary, but I clustered into like three different ways. One being Trotter product formulas, which are simple, yet in some sense limited to early times for the current level of the hardware, which is pretty significant. And so you can only execute certain finite depth circuits. And since the Trotter product formulas would increase in depth as you go for longer time, this kind of limits the amount of time you can reach. Now, the algorithms with the best asymptotic scaling, as have been discussed at length, they often have a significant overhead. So in this talk, I will not consider them further. But of course, if this overhead becomes manageable, then these are probably our methods of choice. And so there's a third class of methods that hasn't been discussed so much, which are basically tailored specifically to the NISQ era, where they work with a fixed gate depth. These are hybrid quantum classical variation methods. And the idea is that you trade the gate depth for doing many measurements on the QPU. And there are several versions of this, one of them being this McLachlan simulation, where you kind of propagate the variation parameters of your variation ansatz using an equation of motion, where the coefficients of this equation of motion, the matrix M and the vector V, are being obtained on the quantum device. So now here in this talk, I want to combine, and this was also mentioned in Nathan's talk, I want to combine two methods. And here I want to combine the simplicity of the Trotter product formula with a variation approach to simulate for longer times. And so we kind of like give an initial demonstration of this algorithm on IBM hardware, even though it's for a very small system. But I mean, at least we're showing that in principle, this method can work. Okay, so what is the key idea of this algorithm, which is called Variational Trotter Compression algorithm? The idea is you first propagate a state, for example, the initial state or a previously produced variational state. You propagate it in time using the Trotter product, and then you try to compress it. You update the variation parameters by optimizing a fidelity cost function. So defining this fidelity cost function, which basically first prepares the state at time t, the variation state at time t using this unitary, then it propagates it, and then it reverses this again using updated parameters theta t plus tau that you want to find by minimizing this fidelity cost function. So in practice, you have to perform a quantum circuit like this, which has two variation unitaries and a Trotter unitary in the middle. And for concreteness here, we are considering a variational state of this form, which is a layered form, and we have like n parameters per layer and L layers. And the idea is this cost function has a very easy interpretation. It's just a return probability to the initial state, and it is maximal for the optimal parameters theta t plus tau. So this can be measured on the QPU without any ancillary overheads. You just have to look whether you come back to the right bin if you start, let's say, from a certain product state size 0 here. Okay, so we have applied this to a Heisenberg model, and we used the 1D antiferromagnetic Heisenberg model. We also added a non-integrable term, and the algorithm performed equally well for integrable and non-integrable systems. But here I'm going to discuss results for this integrable model here. So the idea is we start from a classical Néel state, which is not an eigenstate of the Hamiltonian, and then we perform time evolution under this Heisenberg Hamiltonian, which you can think of as a quench if you want. And so the ansatz for our variation ansatz is shown here on the right. It's like a brick wall quantum circuit with odd and even layers, which just has this Heisenberg Hamiltonian in the exponent. So this is what one would call a Hamiltonian variational ansatz. And the idea is, let's first determine the depth of this ansatz that is needed to accurately describe the wave function at some time t. This will of course grow in time, so you need to have a deeper circuit to describe the time evolved wave function. And so we do this by calculating the overlap with the exact state, because we are in a limit where we can still compute with exact diagonalization the wave function psi of t in this point. This is only for us to kind of gauge what layers are necessary. Later in the algorithm, of course, we don't make use of the exact state, because otherwise it would be kind of useless. All right, so here I show the overlap with the exact state as a function of time for different layers of your variational state. And you see that if your layer number is too small, like 2, initially it can of course represent the initial state, but then very quickly the fidelity or the infidelity grows above, let's say, a set threshold of 10 to the minus 4. And so but you also see that if the layer number is large enough, then you can basically represent any time evolved state, and up to here shown to time 4, but also this works to longer time using this variational state. So there should be a possibility to compress that time evolved state into this variational form. Maybe even more interesting is like how this layer, the layer number L star, which is necessary to get like a fidelity below 10 to the minus 4, how it grows over time. And we see that initially it grows linearly in time, and this is actually also the regime where this algorithm may eventually be used, because we also can show that the long time behavior, actually the layer number grows exponentially in system size, but the linear growth initially is also pretty generic. Okay, so now that we have defined we have figured out the layer number L star we need in order to propagate to long times, we can now run the algorithm. We did this on statevector, on CHASM, and on the IBM machine. And so here's the result for statevector. And just to see what we are showing the fidelity, which is the overlap with the exact solution as a function of time. And there are lots of curves here. So let me walk you through this. The first one is the orange curve, which is the Trotter simulation with a fixed time step delta t. And you see that the fidelity remains relatively high because I'm choosing a small time step, which is 0.2 over j. And of course, I can make this error smaller by choosing a smaller time step. Now, in contrast, the gray curve is a Trotter simulation with a fixed number of Trotter steps, which means you have to scale delta t to like larger values to reach longer times, and that's why the Trotter error occurs, accumulates, and this curve decays to 0 at some point. And so now this green line is the Trotter compression, variation Trotter compression, which has a fixed gate depth. So you never execute anything longer than a circuit that's longer than the one that you use to produce the gray curve. However, you're able to simulate unto much longer times. And this is, of course, at the cost that you have to run an optimization algorithm at every time step where we propagate over between these black crosses here. And so this is basically you're gaining something, but you also have to do this optimization, which ultimately becomes more difficult as you have more variation parameters. Okay, I'm running a bit out of time, but let me just say that we have also simulated this in the presence of shot noise, and we're able to run the algorithm pretty well also in the presence of shot noise. Here we're only able to do it for smaller systems, so I should say this is the system size. Yeah, so this was for a system size of 11. This is for a system size of 6. So it is feasible, but these are not terrific system size. I'm aware of that. And then on IBM hardware, we were able to do it for m equal to 3, and the layer number of 2 is necessary here. So this is of course a small system, but you also have a lot of noise. So actually being able to run this optimization at every time step and getting a decent fidelity in the end, which is close to, let's say, 90%. Whereas if you run the full circuit if you just run the plain Trotter circuit, you would end up with a fidelity of about 0.4. So this is an explicit demonstration that this can work. You can simulate dynamics beyond the coherence time on present day devices. Actually, the number of measurements that we needed here were about 5,700. So this was kind of doable over a couple of days. So in summary, is that, I presented this Variational Trotter compression algorithm that was actually devised also by others. I should have said this earlier. So this was something that was proposed also by Giuseppe Carleo and Frank Paulman before our work. And so we can, in principle, simulate out to arbitrary long times with high fidelity if we're able to run that optimization. So it effectively is a Trotter simulation with a fixed step size and fixed gate depth. So this is, of course, a pretty good situation in principle. We have done an explicit demonstration, and let me just mention in the last 10 seconds that the main limitation, of course, is the growth of the number of variation parameters with system size and with time. And so I think the main, like moving forward, we want to confine ourselves to larger systems and concentrating on the short time behavior where we find this linear scaling of the required layer depth with a number of parameters. And so this is better than if you run, let's say, a tensor network approach where the number may scale exponentially, I should say. All right, thank you for your attention.
So maybe we can take a question from the audience. Andrew.
Hi, Peter. I'm wondering how, because you have to do this repeated optimization step by step, how does the error grow as a function of step there?
When you mean the optimization? Well, you can see that
the way I'm thinking of it is you do an optimization to get your first step,
right?
And you optimize based on results from the first step, which already have an error.
Right. So this is what you see here: the difference between the green curve and the orange curve. So ideally, when the optimization you would do perfectly, you would follow the orange curve, but you don't. So there is a small, so the difference between green and orange is basically due to the difference, due to the imperfect compression, due to the imperfect optimization. And you see this becomes, of course, like more significant as you have more noise in the system. So then, sometimes even, it looks like the system comes up with a solution which is better than the perfect compression, but this is only going to happen for a small system. But here you can see that the compression didn't work optimally. So here actually these red dots are the compression, the final value of the compression, how good we are doing this. And you see that in the presence of hardware noise, this is still about 90%, but it's obviously much better with state vector, where this is more like 99%. But this is kind of the answer to your question.
Thanks, Peter.
Thank you, Peter. So we should move to the next one.
Do I see the microphone? I think this. I think I control it. Okay, thank you very much. Can you hear me?
Yeah, short.
And how do I see the slides?
With this.
Okay.
Can people in Zoom see the slides? Just check.
Yes.
Yes.
Thank you.
And here. Okay, yeah, so thank you very much. I'm going to talk about an algorithm for preparing thermal states in a quantum computer. So this is where you can find the details in this archive posting. And these are the people we can talk to learn more about it. Rolanda and Gopi are here today. And I think Zoe might be in person here during 2 days. And Burak has since joined PsyQuantum. Okay, so the problem we are trying to address is preparing the thermal state of a Hamiltonian, H1, target Hamiltonian, which acts on n qubits at some temperature, inverse temperature beta. And we want to approximate this state with some error epsilon. So some of the previous approaches for this problem actually were trying to prepare a purification of this mixed state. And they were trying to do this by starting from an initial state that's a maximally entangled state between two systems and two subsystems. And here, this maximally mixed state, you can write also in the basis of the eigenstates of the Hamiltonian. when you look at the, when you trace out one subsystem, you get the maximum mixed state that doesn't know anything about the target Hamiltonian. And schematically, the algorithm to prepare the purification of the thermal state, which is given in the very bottom, is by acting on one of the two subsystems with this exponential operator, e to the minus beta h1 over 2. And of course, this operation is not unitary. And as Nathan covered really nice in his talk, this can only be implemented by embedding it in a bigger unitary in a probabilistic way. But at the end, when that succeeds, you get the purification of the thermal state of the target Hamiltonian. And by which I mean that when we trace out the second copy, we get the thermal state. Okay, so how is this exponential operator implemented? Poulan and Wojciech have done this using quantum phase estimation, and later Chaudhary and Soma have done this using linear combination of unitaries. And they got algorithms with these complexities. And here, the dominant contribution to the complexity comes from this quantum amplitude amplification step that's necessary to boost the probability of success of implementing this non-unitary operation, this exponential of the H1. So in this work, we improve upon this complexity by doing two things. One, we are considering a better starting point. So the maximally entangled state, as I said, doesn't know anything about the target Hamiltonian H1. So instead, we are going to start with the purification of the thermal state of some nearby Hamiltonian H0. And whenever H0 and H1 are close, we will see significant improvements in complexity. And the second aspect will be to use a non-equilibrium process to further reduce this complexity, which I will get to. Okay, so the inspiration for this algorithm is these non-equilibrium fluctuation theorems, of which Jarzynski equality is one that's most relevant. So I will very quickly give you an idea of what it is. So in this setting, you prepare a thermal state of a Hamiltonian H0. That's not our target Hamiltonian. It's a nearby Hamiltonian, let's say. And then we do a measurement of energy. And we obtain a value epsilon 0n, which also collapses the wave function to that pure state. And this outcome comes with a probability that's given by the Boltzmann factor. And then we evolve the system with some unitary, which we refer to as the non-equilibrium process, because after that evolution, the system is not in the thermal equilibrium anymore. And then we do a measurement of the target Hamiltonian H1. And we find the value epsilon 1 n. And this value occurs with some probability given by this transition matrix element. And finally, we call the difference between the two energy measurements we did work. That's the definition of work. And Jarzynski equality states that if we average over the exponentiated work, e to the minus beta work, that gives us the ratio of the partition functions of the two thermal states, H0 and H1. Or in other words, it gives us this exponential of the free energy difference. So the important thing to notice here is that we only access the thermal state of the initial Hamiltonian H0, and we were able to say something about the thermal state of this other Hamiltonian H1. And this exponential of work was the crucial thing that sort of connects the two thermal states. So that's what our quantum algorithm will be sort of building upon this intuition. So this is the picture representation of the now quantum algorithm. We start with the purification of the thermal state of the initial Hamiltonian H0, given here. We act on this on one of the registers with a non-equilibrium process U, which is an arbitrary unitary. Then we act on both registers with an exponentiated work operator, where the work operator is defined as the sort of difference between H1 and H0, except H1 and H0 act on the two different copies. And H0 has a complex conjugation on it. And at the end of the protocol, we apply this star of the unitary again. And what we get at the end is the purification of the target Hamiltonian thermal state. Okay, so one important thing to note is that this holds for any unitary U, so that will be something we can optimize over. And what this achieved was that compared to the previous approach, is that instead of now having to apply e to the minus beta h1, we only have to apply e to the minus beta work. And this is the intuition that this might be easier, is that if h0 and h1 are close to each other, that work operator might have a smaller norm. And it might be easier to implement this non-unitary operation compared to e to the minus beta h1. Okay, so but we won't actually exactly implement this exponential operator. Instead, we are going to approximate it with this operator we call x. And again, as in Nathan's talk, x will be implemented not directly, but through either a method of linear combination of unitaries or quantum signal processing. And because this will only be implemented probabilistically, it's not unitary, we will also do many rounds of amplitude amplification. So this is the algorithm in a picture form. So the most crucial aspect is now how are we going to do this approximation? So the first crucial ingredient in there is that we observe that we only need to approximate this exponential operator in part of its spectrum that corresponds to values above a certain low work cutoff. And the condition for that is given in that expression that depends on the probability distribution of work. And since we could use any random non-equilibrium process, any arbitrary non-equilibrium process, we can choose it to sort of engineer the probability distribution of work in a way that we can put a cutoff at higher values. So we don't have to work too hard to approximate this exponential. So how we do this X operator is by approximating the exponential in part of its spectrum, right? And then not so good in the other part by this function h of x. And the benefit of this is that in the Fourier domain now we have very fast decaying tails. So when we represent x in terms of is a linear combination of unitaries, where each unitary is essentially a quantum simulation with work operator acting as a Hamiltonian. We find that the sum of the weights in the very bottom add up to something that scales like e to the minus beta cutoff work value. So in Nathan's work, you might remember, this is sort of the quantity that classifies the difficulty of doing this, implementing this linear combination. And in this case, this corresponds to having to do a number of amplitude amplification rounds that scales like e to the minus e to the beta, change in free energy between the two thermal states minus the work cutoff. So then the complexity of the algorithm is dominated by this work cutoff value. So we have some rigorous results in different settings for bounding this work cutoff. For commuting Hamiltonians, we found that this work cutoff cannot be more than the norm of the negative norm of the perturbation, which is the difference between the two Hamiltonians. For local Hamiltonians, we have a slightly looser bound, and then for general Hamiltonians, we have the most loose bound. But maybe most easy to see is that when we translate how this bound on the work cutoff translates into the amplitude amplification rounds, we find that now it always scales like e to the norm of the perturbation. So this is to be contrasted to previous work where complexity was scaling like e to the norm of the target Hamiltonian. So whenever the norm of the perturbation is much smaller, we have an advantage. Okay, so I'm running out of time. So the main result is that we found a quantum algorithm that uses fluctuation theorems to reduce the complexity of the thermal state preparation algorithms. And it should be useful whenever it's easy to prepare the thermal state of a close by Hamiltonian. So yeah, some open problems are proving better bounds on the work cutoff and finding better non-equilibrium processes that will reduce this complexity. So with this, thank you.
We're a little bit late, but maybe we can take one question.
Yes, there is a question.
Okay. So the question is, does the hardness of implementing this algorithm scale with beta, imaginary time?
Yes, it does scale with beta, and that complexity is the same as the previous approaches, so roughly square root of beta. And it's also there's the exponential, right? So the beta appears in the exponent in the slide on the top. And there's some additional sub-exponential dependence.
All right, well, thank you, Igit. So let's jump to the next training talk by Wang.
So I think the next speaker is on Zoom. So yeah, and Wang, you can share slides. Oh, it's here. Okay, they told me. Sorry. Okay. So you didn't share your slides with us, right?
I'm trying to.
Okay.
Can you just button the?
It's probably better you should just share your screen with Zoom. Are you in Zoom?
It's iPad. I don't know how to share.
That's the other option. I think maybe, I mean, we see something, but it's not.
It's coming.
Okay. Right.
Great, you come to me.
Great. Right. Yeah.
So, hi everyone. I'm going to talk about the quantum algorithm for the ground state. The quantum algorithm for the ground state preparation and Green's function calculation in the many-body system. I will show since this is a lightning talk, I will just show you the essence of the algorithm and the actual bounds and numeric simulation can be found in this publication, the imprint of this one. And so yeah, so what is many-body Green's function and why do we want to calculate it? So it's a type of response functions. And what is of particular importance for kinetic matter system is the single particle or quasi-particle Green's functions. Defined by the trace of the quasi-particle creation and annihilation operators over a density operator, either finite temperature or ground state density operators. So the propagator is dressed by the self-energy of the single particle mode in the space-time. So this description is more concise than the wave functions because the exponential Hilbert space dimensions is replaced by the resolution of the space-time variables x here. So exact Green's functions are as hard to compute as solving the many-body Hamiltonian spectrum. But however, there's many extensive number of classical techniques that you can use to calculate the approximate Green's functions, such as Feynman-Dyson perturbation theory. In fact, you can sum over the divergent, the Feynman diagrams, you treat the Hamiltonian that actually is divergent in each term. For example, the Kroll interaction in the long wave distance limit. In that case, the Dyson series expansion discussed by Nathan Weber won't apply because you cannot cut off the Dyson series. But here I will just talk about the quantum algorithm simulation of the Green's function for finite system. And there's two main tasks in computing the Green's function. First one is the ground state propagation, and second one is time evolved the system to measure the state vector. And both tasks we complete with the linear combination of unitary based method, which is based on the fault-tolerant hardware. And here I will just show you the essence of the algorithm. The first part is the ground state propagation part. And we try to construct a ground state projecting operator e to the minus t square h square over 2 using this integral transform, typically used, it's called a Hubbard-Stranowi transformation. And it's typically used to decouple the interacting system into the non-interacting system by introducing auxiliary field. Here we use it as a parameter to construct our LCU series. And this is just a generic circuits. Here I compressed those a bunch of auxiliary Y bundles into the single Y here. And I'm showing here a cartoon picture of how we apply these projective operators onto initial tri-state and projected on the ground state. Particularly interesting is if we have frustration-free Hamiltonian, we can actually construct a thermal density operators instead of h square, and using the one of the algorithms mentioned in the previous talk from the 2017 by Chodhari and Soma. And so since this is a unified framework, the second part is to construct the Green's function directly in the frequency space. We incorporate it using the resolvent, so-called resolvent operators. As you can hear, we apply the Fourier Laplace transform. We focus here, there's a small imaginary part. We will apply the transform slide away from the real axis. This part, omega broadening, mimics the actual lifetime of the quasi-particles. And you can see both algorithms can be unified using the ASU. So just like Nathan mentioned in the morning, you can actually do anything with ASU. Here on the bottom right is a more specific construction of the circuits for the resolvent operators. So this is the application of the ASU and computation of the Green's function using the fault-tolerant hardware. And we can also apply adjust our algorithm and incorporate some details to tailor to the NISC device. Here, for the NISC, for calculating the Green function on the NISC device, we first realized the LCU-based algorithm proposed to exploit the four quantum advantages promised only by the fault-tolerant devices. But for the NISC device, we can find some practical and meaningful applications with Green's function calculations. For example, calculating the embedded, the Green's function for the embedded impurity system, which typically is a small system size. And one of the theorem called dynamic mean field theory solve this interacting many-particle system on the infinite lattice by mapping it to single impurity models. And here's this reference. You can read about further calculation, the full details of this NISC application. But And the two tasks mentioned for the fault tolerant device now are divided by step 1 and step 2. The step 1, we use the conventional variational method to prepare the ground state. And step 2, the time evolution part, we use a cardon-based fast forwarding circuits. So this is one of the methods which is not in the 4 category mentioned in Nathan's talk. And I'm showing you a phase diagram actually computed using the Green's function solved on the actual IBM hardware. As you can see here, we have the horizontal axis is the interaction strengths, and we have a critical interaction strengths that we obtained from the Green's functions, showing from metallic states to insulating phase transition here. Yeah. Okay, that's my talk. Thanks.
For questions maybe from the audience. So I have a question.
Yeah.
I mean, this, applying this exponential to project the ground space, right? Operator, the exponential.
Yeah.
I mean, if you're thinking, you need all this linear combination of unitary stuff, and that seems to be complicated for NISC devices. I mean, is there a way of doing this like in a semi-classical fashion? See what I mean? Like maybe you can use the decomposition that you have, but then add the terms like classically or something like that. Have you thought about it?
So this is a non-unitary operators. To implement it, the typical way is to do block encoding of this one on yeah, I don't know.
Have any other questions from you guys? The chat, I don't see anything. Okay, Norm has a
I
question.
don't know too much about this particular ground state preparation, but is the success of the LCU equal to the probability of overlap of the ground state or related to that?
Yeah. So it depends on the initial overlap, and this algorithm has to estimate the ground energy first to a certain degree, so that the norm of the operator is not too small.
Can you just use like Hartree-Fock energy, or do you have to do that on the quantum?
You can, but you can also use this method by itself. You can first get approximate projected state and then do an iterative loop.
All right, okay, so let's thank all the speakers one more time. So it's a workshop, take it to discuss with other people.
Before we all head off, we're going to first, before we eat and we're hungry, we're going to get group photo.